Hello dear students, in previous video we learned about electric field and electric field lines. From that we discussed what is the meaning of electric field and what is the meaning of electric field lines. And also we studied some properties related to the electric field lines. Now let us discuss the electric field due to a system of charges. Electric field due to a system of charges. Dear students, in previous video we discussed about superposition principle. Right? By using superposition principle, we determine the force acting on a charge due to the system of charges. Right? So using superposition principle, here also we are going to discuss the electric field at a point due to the system of charges. Now let us see how to find a electric field at a point, some point due to a system of charges. See here, I am considering one point in a space. That point is taking as a point P. And here I am taking, there are three system of charges. Here first charge I am taking as Q1. Okay, and second charge I am taking as Q2, and third charge is taking as Q3. Here all the charges are positive charges. Okay, and these all three charges are separated at some distance from point P. Okay, now I am going to take R1 vector as the displacement vector. R1 vector as the displacement vector from charge Q1 to point P. And R2 vector be the displacement vector from charge Q2 to point P. Okay. And R3 be the displacement vector from charge Q3 to point P. Now I want to find electric field at point P due to these three system of charges. To find electric field at point P due to the system of three charges, I am using here superposition principle. So due to the superposition principle, it tells that the electric field at a point due to the system of charges is equal to the vector sum of the electric field due to the individual charges on that point P. Okay, so that is the way of finding the electric field at point P due to the system of charges. Understood? So here I am taking E1 vector be the E1 vector is the electric field acting on point P due to charge Q1. So E1 vector is taking as a electric field at point P acting on point P due to the charge Q1. Similarly, I am taking E2 vector as the electric field acting on point P due to charge Q2. Okay, so E2 vector be the electric field acting on point P due to the charge Q2. Similarly, another charge also there. The third charge also produces electric field at point P, and that one is taking as E3 vector. Okay, so E3 vector is nothing but a electric field acting on point P due to charge Q3. Okay, now I have to find electric field at point P due to these three charges. To find electric field at point P due to these three system of charges, I should use superposition principle. According to superposition principle, see here, electric field at point P, that is I am taking as E vector, is equal to vector sum of the electric field due to the individual charges. Vector sum of the electric field due to the individual charges means due to Q1 I am taking electric field as E1 vector. So E1 vector plus I have to take vector sum electric field due to the charge Q2 on P is nothing but E2 vector plus electric field due to the charge Q3 on P is nothing but E3 vector. Like that I have to take the vector sum of all the electric field due to the individual charges acting on this point P. Okay, so this is the way of find the electric field at any point due to the system of charges. Now let us discuss the concept electric flux. Electric flux. This is a very important concept and it is denoted as phi. Electric flux is a concept which is related to the electric field and surface. Okay. Now let us see how to define a electric flux. So electric flux over a surface. Electric flux over a surface is defined as the total number of electric field lines passing through that surface. Then it is called as electric flux. So electric flux over a surface is defined as the total number of electric field lines passing through that surface. So that means, see here, now I am going to consider one surface area. Okay, so this is the one surface and this is the surface area. Okay, and that surface area is I am considering as S vector. You know that area is a vector quantity, right? So this is the surface area and that surface area I am considering as S vector. And this surface area I am placed in a uniform electric field. So what is the meaning of uniform electric field? So uniform electric field means its magnitude and direction is same. Then it is called as a uniform electric field. See here, if you observe here, the magnitude of this electric field is same and direction also same. Then it is called as a uniform electric field. And this lines indicates that electric field lines. Here we are indicating the electric field in terms of electric field lines. And suppose that these electric field lines which is passing through this surface area, then we are calling it as electric flux. Okay. If more number of electric field lines are passing through this surface area, then we consider electric flux also more. Understood? If less number of electric field lines passing through it, then the electric flux through that surface also less. Understood? Now let us see how to find the electric flux through this surface area. To find the electric flux through this surface area, I am considering small area element in this surface. Okay? Here I am considering the small surface area element. Let us assume that this is the small surface area element. And through this small surface area element also the electric field lines which is passing. Now I am going to find this electric flux through this small area element. And this small area element I am taking as delta S vector. Okay, delta S vector. So delta S vector is the small area element. S vector is the overall surface area. Understood? Now how to find the electric flux through this small surface area element? So here, thus electric flux through this small surface area element is taking as delta phi. Okay, delta phi. That is equal to dot product of electric field and surface area element. So using this formula we are going to find the electric flux through this small area element. It is the dot product of electric field and surface area element. Understood? See here, if you observe here, electric flux and electric field, they are directly proportional to each other. If the electric strength of the electric field through this area element is more, that means if more number of electric field lines pass through this surface area element, then electric flux also more. If less number of electric field lines which is passing through this, then the electric flux is less. Understood? So this is the way of finding the electric flux. Here we are using the dot product of two vectors. Now how to find the dot product of two vectors? We know that from class 7th, the dot product of two vectors is nothing but it is the product of magnitude of two vectors. How to take the product of magnitude of two vectors? See here, product of magnitude of two vectors. Here two vectors is nothing but electric field is the one vector and surface area vector is the another vector. We have to take magnitude of two vectors and also we have to consider the product of that two vectors. Okay, product of magnitude of two vectors and the cos of the angle between them. Then it is called as a dot product of two vectors or scalar product of two vectors, or it can be written as a delta phi is equal to E delta S cos theta. Here if you observe the theta is nothing but the angle between E and delta S. That means it is the angle between electric field direction and surface area element direction. Then how to find the angle between electric field and surface area vector? To understand that, see here I am considering one surface. Now this is the surface which I placed here. If you observe this surface, this is the face of this surface which is in front of you. And you should consider the face of the surface or area of the surface which is in front of you. Now you should take the direction of this surface area from this surface to your side. Okay, that means now its direction is like this. Suppose that if I place same surface here, for me its direction is like this. Okay, that means the direction of surface depends on from where you are observing, and you should take the surface which is in front of you. Okay, suppose that now assume that this is the surface position of the surface and the direction of surface area is like this. Now some electric field lines which is entering to this surface and passing through this surface like this. If you observe the electric field direction, the direction of electric field like this, and already we know that the surface area direction also like this. Now the angle between the surface area direction or surface area vector direction and electric field vector direction is same. That means both the directions are parallel to each other. Then the angle between them is 0 degree. In that case, I can write delta phi or electric flux as E delta S cos 0. That means the angle between the electric field and surface area vector is 0. The directions are same directions. Then I am taking an angle as 0 degree. We know that cos 0 is 1. Then delta phi is equal to E delta S. This is the electric flux which is passing through this element. Understood? Suppose that if I tilt this surface like this, okay, I am tilting this surface like this, then its direction also changes like this, right? Then electric field lines which is entering to this surface reduces. That means there is a less possibility of a passage of electric field lines through this surface. If I tilt like this, then the direction of this surface like this. Then the possibility of electric field lines passing through this surface is less. Right. Now the electric field line direction is like this and surface area direction is like this. That means electric field direction and surface area direction are perpendicular to each other. Then angle between electric field direction and surface area vector direction is 90 degree. In this case, I can write electric flux as delta phi is equal to E delta S. Delta phi is equal to E delta S cos 90 degree. In this case, the angle between the electric field vector and surface vector direction is 90 degree. Then we know that cos 90 is equal to 0. Then delta phi becomes 0. That means there is a less number of passage of electric field lines through this surface. Okay, so that is about the electric flux. So then I can write the electric flux through this surface is 0. That means the less number of electric field lines passing through this small area element. So this is for a small area element. Suppose that if I consider overall surface, then how to find the electric flux through this overall surface? So that electric flux through overall surface can be determined as a summation of this one. Summation of this one, we will get the electric flux through this overall surface area. Or we can integrate this, then I will get the electric flux through this overall surface area. To get the overall surface area, for overall surface, electric flux can be written as a summation of delta phi is equal to summation of E dot delta S vector, summation of E dot delta S vector, or summation of delta phi is equal to summation of E delta S cos theta, E delta S cos theta. Suppose that theta is equal to 0 degree, then I can write summation of delta phi is equal to summation of E delta S. Summation of delta phi I can write phi. For overall surface I can write phi. And we know that electric field is a constant here. That's why I am taking out and I am taking summation of delta S. So this is a way of finding the electric flux for an overall surface. Okay. And you should remember that this surface area direction which is always perpendicular to this surface. That means if surface area direction is like this, then the direction is perpendicular to this surface. See here, this is the surface and this is the direction. And angle between this direction and surface is exactly 90 degree. Okay. So that is about electric flux. So electric flux is nothing but electric flux over a surface is the total number of electric field lines which is passing through that surface. If more number of electric field lines passing through that surface means then the electric flux also more. If the less number of electric field lines passing through that surface means electric flux also less. That means it depends on how many number of electric field lines passing through that surface. Okay, and see here, we know that electric flux is nothing but it is the dot product of two vectors. We know that the dot product of two vectors is always scalar or scalar quantity. We are calling it as a scalar quantity. So that here dot product of two vectors is always scalar. So we can tell that electric flux is a scalar. Electric flux is a scalar quantity. Scalar quantity. And what is the SI unit of electric flux? SI unit of electric flux is the SI unit. We know that SI unit of electric field is Newton per coulomb. Newton per Coulomb, and SI unit of surface area is a meter square. So that the SI unit of electric flux Newton per Coulomb meter square. Then what is the dimensional formula? Now let us see dimensional formula for electric flux. Dimensional formula. We know that a dimensional formula for electric field is nothing but, so dimensional formula for electric flux we can written as a dimensional formula for electric field is M L T minus 3 A minus 1 into dimensional formula for surface area, that is nothing but L square. We are taking length square L square. Then dimensional formula for electric flux is nothing but M L cube T minus 3 A minus 1. Okay. So this is the dimensional formula for electric flux. So that is about electric flux. Now let us discuss about the electric dipole. Electric dipole. See here, the name tells that dipole. The dipole means here, di means two poles. Then what is the meaning of electric dipole? Electric dipole is nothing but a pair of equal and opposite charges separated by a small distance. Then it is called as electric dipole. A pair of equal and opposite charges separated by a small distance is called electric dipole. Now let us see what is the meaning of electric dipole. See here, I am considering one positive charge. Assume that this is a positive charge. And similarly, I am considering another charge, that is a negative charge. Okay. One is the positive charge and another is the negative charge. And the magnitude of both the charges is same, but the polarity of these charges are different. And if you observe, these charges are separated by a small distance. Okay, there is a distance between the two charges, and there is one center between these two charges. Okay, that center I am taking as P. Okay. And there is a length or distance between these two charges, which is called as the length of the dipole or dipole length. Dipole length. Or it is also called as a dipole axis. Dipole axis. This line called as a dipole length or a dipole axis, and the center between these two charges, that is called as a dipole center. Dipole center. Here I am taking the distance from positive charge to that point P as A, and similarly I am taking the distance from negative charge to that point P as A. Then the total length between two charges is nothing but 2A. 2A. That is the electric dipole. Here the equal and opposite charges are separated by a small distance. That means, for example, if I take this positive charges plus 5 coulomb, then negative charge I should take 5 coulomb, but that charge should be negative. That means if you observe, the magnitude of both the charges is same. That means the magnitude here is 5, but 5 coulomb, but the polarity is different, and there should be a distance between these two charges. And you should remember that here the total charge due to the electric dipole is equal to 0, because here, see here, it has one positive kind of charge and it has another negative kind of charge, and there is a small distance. But both the charges are not same kind of charges, they are opposite kind of charges. We know that if one positive charge and another negative charge is there, then the total charge becomes 0. Similarly here, the total charge of this electric dipole is 0, but the electric field due to this charge is not equal to 0, because here there is a small distance between these two charges. So that the total electric field due to this electric dipole is not equal to 0. Only the total charge due to the electric dipole is equal to 0. Understood? So that is about the electric dipole. And another concept is there that is related to the electric dipole. That is nothing but the electric dipole moment. Electric dipole moment. Electric dipole moment of a electric dipole is defined as it is the product of magnitude of one of the charge and distance between them, then it is called as electric dipole moment. It is a product of a magnitude of one of the charge and the distance between them. The magnitude of one of charge, that means, see here, suppose that if I take one charge as plus 5 coulomb, another charge is minus 5 coulomb, the magnitude I should take only as 5. Okay, I should take only the value of that charge. And if I multiply that magnitude of that charge with the distance between two charges, that is 2a, then I call it as electric dipole moment. That can be represented as a letter P. And this electric dipole moment has a direction, and its direction is always from minus charge to or negative charge to positive charge. Its direction is like this, always from negative charge to positive charge. So that it is an vector quantity. That means electric dipole moment has both magnitude and direction. So according to electric dipole moment, it tells that it is the product of magnitude of one of the charges. I should take a magnitude of any one of the charges, that is Q, into the distance between two charges. Distance between two charges is nothing but 2a, right? 2a. And it has a direction, and that direction I am representing using the unit vector, that is the p cap, which represents the direction of this electric dipole moment, and its direction always from negative charge to positive charge. So that is about electric dipole moment. And the SI unit of electric dipole moment is SI unit of electric dipole moment is, see here, the SI unit of here charge is coulomb, and the SI unit of length 2a means here it is the distance. Distance means that is the length between the two charges. That one is nothing but meter. Therefore, the SI unit of electric dipole moment is coulomb meter. And the dimensional formula for electric dipole moment is, see here, you know that dimensional formula for charge, that is nothing but ampere and time, right? Ampere, time is T, ampere is A, multiplied by the length. The dimensional formula for length is nothing but L. So that the dimensional formula for electric dipole moment becomes LAT. Understood? So that is about electric dipole and electric dipole moment. So very important concept for 1 mark and 2 marks. And here the examples for electric dipole moment, dipole is examples. That means where we observe such a kind of electric dipoles. The examples is molecules of water, ammonium, HCl, etc. In such a molecules we will observe the electric dipoles. That is the molecules of water, ammonia, HCl and etc. That are the examples for electric dipole.